Hi, it's me, Dr. Prasad Puthiyillam. Continue my class on magnetochemistry of coordination compounds. In previous class, class 1 to 5, explained about the introduction to coordination complexes, and then D block elements, 5 block elements, that is transition metals, then ligands, strong field ligands and weak field ligands, then type of magnetic behaviors, paramagnetic, diamagnetic, ferro, antiferro, and ferrimagnetic properties. Okay, so this class, it is the topic of uh, today's class. It is orbital contribution to magnetic momentum. So how orbital contribute to magnetic momentum, especially to become paramagnetic behavior. Before that, previous class we seen that a crystal field splitting in octahedral complex in presence of strong field ligand. Okay, in presence of strong field ligand, we know always strong field ligand will force the electron to pair up, then coming to the higher energy level, because the negative charge repulsion is there. Therefore, pairing of electron takes place. Therefore, with that of a D5 system, 1, 2, 3, 4, 5 pairing takes place, and when pairing takes place to this particular arrangement, we can say that only one electron is there unpaired, and the spin, if you calculate it will be a low spin situation. The electronic configuration of this system is D2G5 EG0, and it is giving a low spin complex. In presence of weak field ligand in octahedral complexes, weak field ligand, the crystal field splitting energy, the energy difference between T2G and EG is less compared to that of in presence of a strong field. Or we can say, in say example with the D5 system, we can say that it is not forcing for pairing. Okay, singly occupying. Okay, from T2G then goes to EG, the electron goes to EG. Therefore, this is a T2G3 EG2 system with a D5 octahedral complex in presence of weak field. It is a high spin situation, or we can say that they are high spin complexes. Then crystal field splitting in tetrahedral complexes, if you discuss. In tetrahedral complexes, the delta T is 3 by 9 times that of delta O, that is that of octahedral splitting energy, crystal field splitting energy. That means tetrahedral splitting energy is very less. Okay, so even if it is a strong field ligand or weak field ligand, the energy difference is less. Therefore, electrons will try to singly occupy than undergoing pairing up. So the field, the ligand field is not contributing towards the electronic configuration here, because only 4 ligands are there. The ligand field is less compared to that of octahedral complex. Even the arrangement of orbitals, they are not pointing towards the charged ligands. Therefore, the energy contribution is less with that repulsive force what is we seen in octahedral complex. I draw the structure of dz square orbital, and it is pointing towards that of the charged center, charged point, that is ligand. So that such cases are not there in tetrahedral complex. Therefore, the splitting energy is less comparatively. Therefore, pairing of electron is not preferred. In case of octahedral complex, we can say that in presence of strong field ligand, pairing of electron is preferred. Weak field ligand, pairing of electron is not preferred. And in case of tetrahedral complex, pairing of electron is not preferred. Okay. So now what is magnetic moment? Okay, so delta T, it is less, therefore pairing of electron is not preferred. What is magnetic moment? Magnetic moment, that is the when we introduce a external magnetic field, how the substance or material contribute towards the magnetic behavior, how it supports, not opposing. Okay, how it support towards the magnetic field, then we call it as it is having a magnetic moment. We know that diamagnetic substances, they are opposing, whereas paramagnetic substances, they are contributing towards that. Therefore, the magnetic moment is determining the tendency to arrange through the magnetic field. Arrangement of electron is contributing towards the magnetic field. Then we call it as having higher magnetic moment. Whereas any substance, if you can take and if an external field is applied, there will be an induced circulation of electrons. When our magnetic field is introduced to a substance, the electrons present in that its spin, that orbital movement, it creates a magnetic field and that is opposing that. Such cases we call it as diamagnetic. That means there are no unpaired electron. All electrons are paired up. That means almost all substances having the paired electrons. The paired electrons are always contributing towards, or it is opposing towards the external magnetic field. Whereas if one single electron or unpaired electron is there, then it will be contributing towards the magnetic field. It will be upcoming, or it will be opposing to the diamagnetic effect, or it will be stronger. The effect is stronger than diamagnetic. It becomes paramagnetic. Therefore, paramagnetism, it is seen when there are unpaired electrons present in a substance. If unpaired electrons are there, it will contribute towards paramagnetism. The spin and orbital motion of this electron give rise to permanent molecular magnetic moment that tend to align themselves with the applied field. I know my video is covering the sentences. It's okay. In the coming slides, no much sentences are there. Okay, therefore, the spin and orbital motion, they are contributing towards the paramagnetic behavior in presence of applied magnetic field. And the paramagnetic effect is much larger than diamagnetic effect. Therefore, even one electron, unpaired electron is there, then also it becomes paramagnetic. It will overcome the diamagnetic behavior, it becomes paramagnetic. And it is present only in presence of the paramagnetism is present only in presence of an applied magnetic field. When applied magnetic field is removed, then it loses its magnetic moment, or it will loses its magnetic property. Okay, so we'll see the examples how the D1 to D10 systems, how they contribute, the octahedral complex, tetrahedral complex, strong field ligand, weak field ligand cases, how they contribute towards the paramagnetic behavior of the material. That we'll see with examples. All cases are explained here, so it will be a little bit long video. Okay, so conditions required to say whether it is a paramagnet or not contributing towards the magnetic moment. The condition, first condition, that the orbital must be degenerated. Okay, already the ground state, we see that all the d orbitals are degenerated, having same energy. In presence of a ligand, where though it goes to higher energy level and there is a splitting takes place, then also the dxy, dyz and dxz, they are having same energy. We call it as T2G or T2 system. Okay, they are having same energy. We can call it as they are degenerated system. They are having same shape, same size, and transformable. Okay, so the dxy, dyz, dxz, they are having same shape, same size, and even we can transform dxy to dyz by rotation, by angle rotation, 45-degree angle rotation. We can convert them, but there should not be any identical spin of electrons in that dxy, dyz, and dxz. If all electrons are having identical spin, then if you try to transform, then the spin will rotate. They are rotating a 45 angle. Therefore, the electron spin also will be opposite. That is not possible. It cannot contribute. Therefore, there should not be any identical spin. Therefore, these conditions we have to keep it in mind. Then we can see the arrangement, the D1 to D10 systems, whether it is contributing towards the paramagnetic behavior or not. So we'll take with we first write the degenerated orbitals T2G as well as EG. Okay, so that is EG. Okay, so we'll take this system D1 system. D1 system is only one electron in the outermost d orbital. Therefore, it will go to T2G. Yes, it is the electronic configuration is T2G1 EG0. Yes, it is contributing towards the magnetic momentum because all orbitals are degenerated. DXY, DYZ, and DXZ, they are degenerated orbitals. They're having same shape, same size, same size, and they are transformable. There are no identical spin, only one electron is there. Okay, therefore it is contributing. D2 system is also contributing. Okay, the D3 system, 1, 2, 3 electrons in T2G, they are having identical spin. So the electronic configuration, what we write is T2G3 EG0, or simply we can write T2G3 only. EG0 need not write. Okay, so it is not contributing because there are identical spin. D4 system, now it is clear to you. D4 system, in presence of weak field ligand, that means there is no force for pairing. The electron will go to the higher energy level, the next electron will go to higher energy level. So the fourth electron go to dx square to y square. Therefore again identical spin cases. T2G3 EG1, that is the electronic configuration. Identical spin is there, it cannot contribute towards magnetic moment. D5 system also the same case with a weak field ligand. It will not contribute towards the magnetic moment. Okay, electronic configuration is T2G3 EG2. In coming classes, I'll be taking example as T2G EG only. I will not write D5 system or weak field ligand, strong field ligand. Those cases will try to avoid it. Okay, so D6 system, 6 electrons are there, 3, 4, 5, and sixth one come here. So D6 system, there is a pairing takes place. So one n-pair orbital is the T2G. T2G4 EG2. Yes, orbitals are degenerated, same shape, same sizes, transformable, but even no identical spin also. Therefore, it is contributing towards the magnetic moment. D7 system, 1, 2, 3, 4, 5, 6, 7 electrons arranged. D7 system also it is contributing T2G5 EG2, that is the case of D7 system with the weak field ligand. Yes, it is contributing towards the magnetic moment. D8 system, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what happened on the T2G level? There are no unpaired electrons on. They are completely paired. So paired electrons cannot contribute. T2G6 EG2, that is the electronic configuration. Unpaired electron is there in T2G. Okay, that is the degenerated orbital. They are the same, having same size, same shape, and transformable cases. Whereas it has having no, there is no unpaired electron in T2G, therefore it cannot contribute towards magnetic moment. D9 system also the same. Okay, that is D9 setup electronic configuration, that is T2G6 EG3. Unpaired electrons are no unpaired electrons, therefore it cannot contribute. D10 system also it cannot contribute because all the degenerate orbitals are having unpaired electrons. No, having paired electrons, there are no unpaired electrons. T2G6 EG4 it cannot contribute. Now we'll see with that of a strong field ligand, that is octahedral complexes in presence of strong field ligand. Strong field ligand T2G1 EG0 case, that is 1 electron, it is contributing. T2G2 is also contributing. T2G2 EG0 is also contributing towards the magnetic moment. D3 system, T3 system, it cannot contribute because there are identical spin. Electronic configurations T2G3 EG0 or T2G3 only. It cannot contribute because there are identical spin in that degenerated orbitals. D4 system, so it is a strong field ligand. Strong field ligand means the fourth electron will try to pair up. Okay, it cannot go to the higher energy level because ligand field, the ligand is opposing the negative charge. Okay, therefore pairing takes place. Pairing takes place means here it can contribute. T2G4 EG0, that is the case. It is contributing towards magnetic moment. D5 system, it is also contributing. These are the 5 electron arrangement. That is T2G5 EG0. It is also contributing. D6 system, 1, 2, 3, 4, 5, 6. It cannot contribute because at T2G there are no unpaired electrons. So it is T2G6 electronic configuration. It cannot contribute towards magnetic moment. D7 system also the same. Okay, D7 system. Okay, once. Okay, there is a mistake here. It should be pairing here. Okay, with the reverse spin. Okay, now 6 and 7. Okay, so D7 system. D7 system. Okay, so this is the case of D7 system. Okay, yes, it is. No, it is not contributing. No, it is not contributing towards the no unpaired electrons. Unpaired electrons. Okay, so there are no unpaired electrons, therefore it cannot contribute towards the magnetic field. Okay. Where am I? Okay. Okay, so D7 system, it cannot contribute. that is T2G6 EG1 case. That also we need to correct. So this is T2G6 EG1. T2G6 EG1 case, it cannot also contribute towards the magnetic moment. Okay. Now D8 system. Okay, D7 system is over. D8 system 2, 3, 4, 5, 6, 7, 8. Okay. So the arrangement of electron is again wrong only. So first pairing takes place, then it goes to the higher energy level. Okay, so it is also not contributing. D9 system also it cannot contribute because the lower level it is filled up. Okay, the T2G system it is filled up, therefore it cannot. Filled up means there are no unpaired electrons, it cannot contribute. D10 system also same, all are paired, therefore it cannot contribute. Now with that of a tetrahedral complex, the arrangement is T2G at lower energy and EG having higher energy, or say E is having lower energy and T2 system is having higher energy. So dx square y square dz square having lower energy, dxy dyz dxz they are having higher energy, they will call it as T2. We are not writing the G because there is no center of symmetry in case of tetrahedral complexes. So delta T is less than pairing energy. That means the energy difference between E and T2 is very lower energy. Therefore, electrons will try to singly occupy first. Okay, so D1 system, E1 T2 0, it cannot contribute because it is in dx square dz square, this energy level. They are not having same shape, same size, and they are not transformable. Therefore, it cannot contribute. D2 system also same, and also the electrons cannot contribute. D3 system that is E2 T21, it can contribute. There are degenerated, they are having same size, same shape, and transformable at T2, no identical spin, therefore it can contribute. T4 system also contribute. D5 system when it comes at T2 level, there are identical spin, therefore it cannot contribute. D6 system, that is it cannot contribute because again the same case, identical spin is there. D7 system also it cannot contribute because identical spin is there. D8 system, it can contribute because there is no identical spin at T2 level in dxy, dyz, dxl, which are the degenerated having same shape, same size, and transformable case. D9 system also contribute. D10 system, it cannot contribute because there are no unpaired electrons. Okay, therefore we can conclude that the contribution of orbital angular momentum, okay, the contribution of the orbital angular momentum to the magnetic moment is not quite so straightforward. Okay, so it will be a little bit confusing. At a stretch, we cannot guess whether the system is contributing or not. We need to write and check. Then, by practice, we can guess whether it is contributing or not. Again, the ligand, strong field ligand to weak field ligand, their contribution also there, so that also a little bit confusing. Therefore it is that's why the statement is given, it is not quite so straightforward system. In presence of a ligand field, the dx square y square and dxy orbitals are no longer equivalent. Okay, they split into two, eg system and T2G system, therefore they split, either go to eg, okay, here the dx square y square go to the eg level, and in case of tetrahedral it go to the T2 level. Okay, the other dxy will be in either E level or T2 level. Okay, therefore they are not identical, they are not equivalent energy level. That we call it as the it is quenched, it is destroyed. Their energy level, it is destroyed by presence of a ligand. T2G and T2 orbitals are not contributing towards magnetic moment if electrons are half filled or filled. Okay, so T2G and T2, these orbitals are, they are the orbitals which are degenerated, having same shape, same size, and transformable case. If it is half filled or completely filled, no unpaired electron, then it cannot contribute. That we see in the examples. The half filled case, if you take, that is T2G3. T2G3 means three singly occupied electrons at the T2G system. Singly occupied means what we said, no identical spin. That was the explanation given there. Okay, so it can be explained like this also. So we cannot rotate to equivalent dyz. If it is in dxz, it cannot rotate to dyz, which is already occupied. And when we try to rotate, the spin is different. Spin is not equivalent. As well as the T2G3 EG0, EG0, T2G3 EG1, T2G3 EG2, T2G6 EG0, T2G6 EG1, T2G6 EG2, T2G6 EG3. These configuration that you already seen, they are quenched. Quenched means they are not contributing towards the magnetic moment. They are destroyed. The electronic configuration is destroying the arrangement of electrons. The arrangement of electrons is such that it is opposing, it is not contributing towards the magnetic moment. Whereas in case of the electronic configuration with 1, 2, 4 and 5 electrons in T2G orbitals, or the configuration T2G4 EG2 and T2G5 EG2, they are contributing towards the paramagnetic behavior or towards the magnetic moment of the substance. So that is about the orbital contribution towards the magnetic moment. Hope you understood the concept. So you can take any examples, any complex. First you need to know which is the central metal atom, its oxidation state you need to calculate. Then you need to write the ground state electronic configuration. With that ground state electronic configuration, you need to see whether the ligand is strong field ligand or weak field ligand. You need to arrange the electronic electrons in such a way. You need to write the electronic configuration. Then with that you can analyze whether it is contributing towards the magnetic moment or not. Okay, so thank you very much for watching my video.